Hello. So today we're going to be talking about dielectric resonating antenna, or just DRA for short. So DRAs are very flexible, compact, and efficient devices that in an ever-growing age of technology have been seeing more and more use. So why are they so special? So first we're just going to start off by looking at how they work. So here what we have is called the ground plate, and attached to it we have a microstrip. And the microstrip is what actually conveys the information from a signal to your resonator. And your resonator is a dielectric, that's why it's called a dielectric resonator. And a dielectric is anything that conducts electricity, or that does not conduct electricity, but also can be polarized. Therefore, it can have influences on electromagnetic fields, but cannot conduct electricity. So examples of this are such things as glass and some plastics, and they're commonly used in real dielectric materials. So when we place the dielectric on top of the ground plate and microstrip, we can see that it emits its information in all directions that are not through the ground plate. So this is a very nice way to see that you can also have different shapes as well. So you could have some things like cylinders or hemispheres. It doesn't really matter, as long as it's a shape, you'll be able to see it. But you can also have things such as swans. So in this case, someone's using a swan as the resonator, and you can see it going through free space to the TV.
A dielectric resonator antenna, or DRA, is a radio antenna. This means that it serves the purpose of converting electrical power into radio waves, and vice versa. The main component of a DRA is some three-dimensional device of various shapes made of some ceramic material. DRAs usually operate in the microwave frequency range, ranging from approximately 3 to 30 gigahertz. In order for a DRA to operate, the microwaves are introduced inside the DRA through something like a probe. Because of the sudden change in permittivity between the dielectric and the air, with the dielectric constant of the DRA ranging from 10 to 100, the waves are confined within the resonator material and start bouncing back and forth off the walls. When these waves reach the resonant frequency, the microwaves begin to oscillate with very large amplitudes. This is optimal for signal transmission. The resonant frequency of a DRA is determined by the overall dimensions of the DRA and the dielectric constant epsilon r. This means that by increasing the dielectric constant, the size of the DRA can be greatly reduced. Considering a cylindrical DRA in particular, if we plot the resonant frequency as a function of radius, we can see that as the radius increases, the resonant frequency actually decreases. This means that in some applications, where a specific frequency is required, be it a very small or very large one, a cylindrical DRA can help to facilitate this required frequency.
We know that DRAs are mainly used with microwave frequencies. And when we discuss microwave frequencies, we know that the average length of a lambda is going to be 10 to the 9 nanometers, and the frequency is going to be 3 times 10 to the 8 hertz. So, knowing this, now let's look at a DRA. So a DRA is composed of a few different things. We're going to have a dielectric, we're also going to have a ground plate, and right now what I'm highlighting is actually your dielectric material. This can be composed of any sort of insulator. And now the arrow I just drew is actually our E field, or our electromagnetic field. And here is our ground / metal plate for our base, essentially. And as I said, this is an insulating material. So what's so special about this is the fact that it has no metal in it as an actual working component. And what this means is that we're not going to have any power loss to our metal. So for many other antennas, we have power loss in any types of transmission that involves a metal component actually being used in the antenna. And what this means is that it could actually handle a higher frequency, which is why it's able to handle microwaves. So that pretty much gives up a sum up of why we're able to use them for microwaves. And also another DRA use is for ground penetrating waves. So basically we use this for high data exchange rate, and that's also a key property. And it's got to go short range, and we're able to achieve this with wireless local area networks. So there's basically two different signal forms that we could use. There's going to be a directional one, which I have on the right, and an omnidirectional, which we have on the left. Omnidirectional just means that it goes and it surrounds, emits from a certain position in all directions. So another use is mobile and portable platforms like cellular phones. So for mobile phones, we know that there's going to be several different requirements that are necessary as design specifications for our DRAs. So they need to be small size, and they also have to require multi-band antennas. And multi-band simply means that it requires, or it takes, two different frequencies that are slightly different. And this small size also goes to connect with the fact that DRAs can be any geometric shape, from cylinders to spheres to rectangles. So this is why they're so easy to design with. And in comparison, this is what a basically radio antenna of something that's not a DRA would look like. It's got to be much larger. It involves a long length for arms and coming off from your coaxial cable. And basically it's not feasible for small cell phones.
The market today demands that these electronic systems are highly efficient and have a wide bandwidth, all while being as small as possible. This is essentially why DRAs make most sense in industry. DRAs are very, very versatile. By properly choosing the correct design parameters such as the geometry, permittivity, and Q factor, DRAs are able to be used in a wide range of applications. Some of these applications consist of the WiMAX, the WLAN, UWB, RFID, and the dielectric wireless receiver, along with many other products that take advantage of DRAs. There are three main types all DRAs fall into: the wideband, ultra-wideband, and the multiband DRA. In these DRAs, there are a variety of other DRAs that fall into each class. Each have different advantages and disadvantages and are better for certain applications than others. It is the ability to create a DRA which is designed specifically for the required product that makes them so appealing to the industry. The lightweight, small, cheap, and efficient properties is what makes them a smart choice for so many products.